So today's lesson we're going to begin chapter 3 in Pre-Calculus 30, and we're going to talk about characteristics of polynomial functions. So from your textbook here, this is the definition of a polynomial function. I'm sure you know what a polynomial is, and a function is basically a f of x or a y equals. So we have a y variable, or the function notation here, and then another variable, usually x. Okay, so what's a polynomial? Well, there are types of functions that are considered polynomial functions that have this as their pattern, and this is a bit tricky, actually, I think, to understand, but I'll try and simplify it for you. Okay, a polynomial function happens when we have an exponent. Okay, exponents here on any of the terms that are whole numbers. All right, so no negatives, no decimals or fractions. Okay, so the exponents are not negative, decimals, or fractions. Now it says here, I don't really like how this is put in your book, to tell you the truth, but it says n is a whole number. Well, if n was 1, then n minus 1 would be 0, and n minus 2, and so on. So this pattern, you have to be real careful here. They do say that, hey, this goes all the way down to where x is 2, and then where x is to the power of 1, and then where x is to the power of 0. But let's just suffice it to say that the exponents, okay, so let me just write this down here. A polynomial function, the exponents on the variable are only whole numbers. So 0, 1, 2, 3, 4, 5, 6. So that means no decimals, fractions, or negatives. Okay? And there is a variable, okay? X is a variable. Now, it doesn't have to have a variable because as you, this isn't on the list, but another example of a polynomial function would be y equals 5, let's say. That's perfectly fine. It's a polynomial function. The x variable is technically there. It just has an exponent of 0. Okay? So if it shows up just as y equals 5, that's a polynomial function because x is a variable that's included, even though it's just to the power of 0. So it's like it doesn't even have any effect, right? Y equals 5, we'll see, you know what that is. That's a horizontal line going through y equals 5. Okay, what else do we need to know? Coefficients are real numbers. All right, so that shouldn't be a big deal, but real numbers are positives, negatives, 0, irrational, rational, anything. Basically, it's anything. It's just not unreal numbers or complex numbers, which you don't even really know about, so don't worry. Okay, so they're real numbers, so it can be anything, positive, negative, decimal fraction. Here are some examples. F of x equals 2x minus 1. That's an example of a polynomial function. F of x equals x squared plus x minus 6. That's an example. Okay, x cubed, y equals 5, as I mentioned as well. So these are all examples. Let's say some non-examples, okay? So what are some non-examples? Well, what about y equals 1 over x? Why is that a non-example of a polynomial function? It's a fraction. I don't know if... I think you could expand on that. What do you mean it's a fraction? Okay, a negative something, yes, we're getting close here. This is actually the same as x to the power of what? Negative 1. Look at that. That's a negative, so this is not a polynomial function. Okay, so when you said fraction, yes and no. You can have a fraction as a coefficient. Like this is okay. 1/2 x. That fraction's okay. But you're right. If x is in the denominator, that's not a polynomial function. And we're going to talk about the types of functions where x is in the denominator. We're going to talk about those in another section. Okay, so that's an example. Okay, you guys tell me this one. What about this? Y equals root x. Is that a polynomial function? Is that okay? Is that good? Yes, no? What do you think? What would the exponent be on x there? That's x to the power of 1/2. So is that okay? No, it's not. It has to be a whole number. So that's not a polynomial function either, per se. Okay? So no decimals, no fractions, no negatives as exponents. What is the degree of a function? Do you remember this? Have you ever been told this? Degree of a function? Okay, it's to the power of, it's the n. Okay, technically you're right, because in this definition, the n is the largest value of the exponent. So that's what it is. Okay, so the degree of a function is the largest value for an exponent of a variable. If I can put it that way, that makes sense. So the largest value for an exponent of a variable. So you could have a collection of terms like this right here, x squared, x to the power of 1. This is 6x to the power of 0, really. So the degree of this one here, right here, is the largest exponent on the variable, which is 2. So this is a degree 2. What do you call a degree 2 function? Square? What's the parabola? Is the shape that it makes? It's a what kind of function, though? X equals negative b plus or minus root b squared minus 4ac all over 2a. That is the what? Quadratic formula. Yes. So a quadratic equation is x squared. Yes, quadratic equation makes a parabola shape. Okay? That's quadratic. All right, so here we go down here. Let's talk about this. These names here have everything to do with the degree of the function. And you'll need to know these names. We don't often speak of quartic or quintic functions. We don't talk about those too much. But a linear function has degree what? 1. So anything with degree 1, if you look back up here to the top of the screen, f of x equals 2x minus 1, that is a linear type function because that makes a straight line. Okay? And of course, we know a lot about this straight line. We know that the x-intercept, or the y-intercept is what? Negative 1. We know that the slope is 2. Right? Y equals mx plus b. Remember that? All right, so linear. Quadratic is here. That's degree 2. Cubic is degree 3. Quartic, so quad, that's kind of the root, quartic is degree 4, and quintic is 5. Okay? So that's all you'll need to know. You might get questions about that, but that's it. All right, so what we're going to do now is we're going to explore these different types of functions. So what we're after is characteristics, right, of polynomial functions. So let's explore these. You all have your graphing calculators in front of you. Okay? And what I would like you to do, okay, so we have 1, 2, 3, 4, 5 of these sections, and I have 1, 2, 3, 4, 5 rows here. Okay? So for each row, this is what I'm going to get you to do. I'm going to get you to graph each function in your row. Okay? So, yes, it gets a little bit long here. Okay? So let's start with this side right here. Yeah, that's right. These poor guys, there's only 2 people in this row, so I'm going to give them the easy job. Okay? So you guys are linear, okay? And quadratic. Actually, these 2 rows are both linear and quadratic. All right? This row is cubic. You guys do the cubic ones. Let's see. How about, let's put you guys in that. So 3 and 4. So you 4 in the back there, including you, Olivia. You guys do the quartic here, and then the rest of you 3 do the quintic. Okay? It won't take you long. But listen, what I want you to do is I want you to graph all 3 or 4 of these at the same time, and then we're going to talk in a few minutes about some characteristics. And we're going to explore kind of what the different things do, and I'm going to do something as well while you guys are working on that. Okay? So we'll join back here in a minute or 2 here when you get that done. All right, so what we're going to talk about with these, you may not have these graphed yet, you may or may not. But look at, in your textbook here, look at point number 2. I want you to look at these graphs, and we're going to talk about the similarities within each set. Okay? We're going to take a look at them all, but I want to discuss end behavior is one of the things, that's one of the main things from this lesson. And if you've never heard of the term end behavior before, look over here. The definition for end behavior is the behavior or what the graph tends to do in reference to the y values of the graph of the function as the absolute value of x. So that is as x becomes really large in the positive direction and really large in the negative. Okay, so the end behavior. What does the graph do? Does it make a straight line like this? Does it go up as it goes to the right? And does it go down as it goes to the left? Or what does it do? You know what I mean? Does it come up, to a certain value? Does it make a straight line, right? Does it, curve up this way and then curve up this way? So the end behavior. So what happens here at the ends, okay? So that's end behavior. Now, the other thing is the degree. So that's pretty easy. We know what the degree is. The constant term. What's the constant term? The constant term is going to be the number that does not have a variable attached to it. Okay? And in a simplified polynomial function, there will only be one maximum of one constant term. Okay? Of each kind of term, there will only be one. So here's a constant, there's a constant, there's a constant, there's a constant. So I want to talk about the constants and what significance they might hold. So again, some of you are asking me, like, so what do these graphs look like? Well, that's what we're going to talk about today. We're going to take a look at what everybody's done, and we're going to talk about, these things. So leading coefficient, what is the leading coefficient? Well, that's going to be the number or the coefficient that is attached to the variable that has the largest exponent on it. So for example, let's take a look at this one right here. Okay? This is a polynomial function. It is degree 4. Why? Because 4 is the largest exponent. That means that this is the leading term. That's the leading term. So if you wrote them in descending order of the size of the exponent on the variable, this is descending order of the variable. It's the first term that's written. So that's a leading term. The number that would be attached here, so in this case it's just a 1, this is the leading coefficient. Okay? So what does that have to do with the shape of the graph, or what the graph looks like? So these are all the types of things that we're looking at. And also, finally, the number of X intercepts. So there's a lot to talk about. And again, it's going to be a discussion where you guys are going to tell me the answers to these ones, and we're going to come across this as a class. All right, so does everyone understand end behavior, degree, constant term, leading coefficient? The number of X intercepts is literally how many times the graph cuts the x-axis. So this one would have 4 in this particular graph right here. See that? Okay? So let's talk about those for a second. Let's take a look at linear first. All right? Y equals x, y equals negative 3x, and y equals x plus 1. End behavior. What happens to the graph when, okay, and I've lit this one up here, okay? And let's say it's 3x to the power of, let's make that a 1. Okay, so there's 3x. All right, here is 1x. Here is negative 1x. Okay, so I'm kind of showing you a little bit about what you might have graphed there. Okay. So the end behavior is what happens to the graph when x gets really, really large. So let me zoom out a bit. The end behavior is the graph, the y values increase steadily and without bound, right? And so the other end is this way. It goes down to, well, it's unbounded, negative infinity. So the end behavior, what you're going to be able to do here now is you're going to be able to say, basically what quadrant the graph ends up in, or what value the graph approaches. So here we're going to say the end behavior for a linear function is for a linear function with, we go back to here, with a positive leading coefficient, okay, because this one has negative. So the end behavior here is starts in quadrant, and what's this quadrant down here? 3 and ends in quadrant 1, okay? So end behavior for linear, okay, with a positive leading coefficient, starts in quadrant 3, ends in quadrant 1, okay? Now, before you write all this down, I'll tell you the truth, I'm going to do a summary later, so don't write this down yet, okay? Let's just kind of explore here for a while, all right? So if we have a negative coefficient, right, like negative 3, do you see how the end behavior changes? The leading coefficient changes that end behavior. If we have a different slope, same end behavior, right? Same end behavior, but just the steepness, the slope has changed, okay? All right, so what happens if we now have a quadratic? Okay, that's a quadratic right there, right? Okay, quadratic. So the end behavior for quadratic, if the coefficient is positive, the end behavior is, you could say, starts in quadrant, what is this one? 2, and ends in quadrant 1. Okay, so end behavior starts in quadrant 2 to quadrant 1. You usually go left to right. Yeah, you say 2 to 1. Okay? If this is a negative value, then what are the quadrants? 3 to 4. Okay? And so that's when this is a quadratic. All right. Now, I want to just light up this one here too, okay? And I want you to see something here. So if A is 2, we have a parabola. Now, everybody just watch this real careful. This is basically y equals x squared plus 2x, because A is 2, and so this is 2 minus 1. So this is x squared plus 2x. That's what this is, this parabola. All right, if I change this to 3, now we're looking at the cubic function. And you're going to have a function that looks something like this. So those of you that did cubic functions, did you kind of have something like this where they kind of started down in the lower left maybe and up to the upper right? And they did something like this in the middle? All right, we take a look at a cubic function like this, right? So this one right here would have maybe looked something like this, except it would have been down lower. Okay, so this is a cubic function. This is a quartic function. Okay, this is a quintic function. Now, what I'm going to do here is I'm going to roll this back, and I'm going to basically let this roll here. So that's a quadratic, cubic, quartic, quintic. Okay, now this is to the power of 6, 7. So do you guys see kind of what's happening here as far as end behavior goes, if we just are looking at end behavior? And I might have to zoom out. It's not the best. Let's zoom back in here. Okay. All right. Okay. So end behavior, it kind of flip-flops. Did you notice that? If it's an odd degree, what can you say about the end behavior there? You see how it straddles the origin, so quadrant 3 to quadrant 1. And if it's an even number, the end behavior is up on the same top half there. See? Even, odd, even, odd, and so on. Okay, question? Back to you guys. What did you notice about the constant term? What did you notice about the constant term here in each of these? Okay, it moves the graph up and down. Yes, that's true. An x squared graph versus an x squared minus 3 graph moves it up and down. Any other observations? No? Did anybody else have any observations? Was there any significance about those numbers that you saw? Okay. Let's put in a constant here. Let's say this is plus 1. Okay, what did that change? It changed the y-intercept. Okay, all right. Now, I'm going to change the degree here, so the degree is changing. Okay, oh, what's going on here? Okay, where is undo? All right, so we got that graph back. What do you notice about this plus 1 here as this changes? If this is just now the constant term, what do you notice on the graph here? Look at that. As we change this graph, the y-intercept is exactly the same for all of them. So what is the constant term? Y-intercept. Okay? The constant term is the y-intercept for any polynomial function. You might want to write that down. Okay? The constant term is always the y-intercept for any polynomial function. Okay, so that constant term, that's very important. Okay, we got to move a little bit quicker here through this. So what about the leading coefficient? How does that affect things? So we talk about, look at this has a positive leading coefficient, this row. This row has a negative. So what did you notice from your first function to your next function here? How did that affect things? And I actually already did that for you too on my graph. It what, sorry? Okay, it flips the function about the x-axis. Okay, what about, let me go, that's a good observation. What about this though? What if I have, now this is my leading coefficient, right? So let's pause it for a second. What if I put just a negative here? Now it doesn't necessarily flip it like a mirror, but what does it do? What changes? Okay, there's that, and this is a quintic function. There's that with a positive leading coefficient, this with a negative. Maybe tough to tell, but what changed? The end behavior. I heard it, yes, the end behavior. It totally changed. Because look at, this is quadrant 2 to quadrant 4 right now. Now, 3 to 1. See that? Okay, so adding a negative here, according to your, that was a good question. Adding a negative here does not just simply flip it about the x-axis, because we are not in the form y equals a f of b times x minus h plus k. We're not in that form. A negative in front, a negative a value would do that, but not just a negative leading coefficient. That just changes end behavior. Okay? Yeah, that's great. Oh, you guys are doing awesome. Okay, now the number of x-intercepts is the last thing I want to talk about here before I throw up the summary screen, okay? But what did you find about the number of x-intercepts? Like, let's look at these ones right here, like the last set D, okay? How many x-intercepts did we have here for this function? Who did that one? Guys, how many x-intercepts for this one? Two, yes, it's a parabola. 2 x-intercepts did you find? Yeah? What about this one? 3? What about this one? How many x-intercepts? 4? What about this one? Was it 5? Okay. So did anyone find any x-intercepts that were greater than the degree? Did you ever find any x-intercepts that were less than the degree? Now, to that question you should have answered yes, because check this one out up here. Okay, if I change this to a plus, and I light this one up over here, okay, and let's make that, oh, I don't know, like 2. The degree now is x squared plus 3, so I have a degree 2, but I have 0 y-intercepts. You see that? So you can have fewer x-intercepts, but you can never have more x-intercepts than the degree. A lot of information here this lesson. Okay, so the number of x-intercepts, the number of possible x-intercepts is the same as the degree of the function. Okay, very good. Okay, that's very, very good. What I'm going to do is I'm going to show you this summary page here now. Okay, so here is the here's the summary. I'm going to go through this. I'm going to take a couple minutes to go through this summary here. This is what we should have uncovered through this little activity. And hopefully you got some of this. But here it is all in one little spot. All right, so a degree 0 function is a constant function like f of x equals 3. So what do we know about that? The end behavior, okay, starts in quadrant 2, ends in quadrant 1. And they say that, you know, it just extends, it's horizontal. It's a horizontal line. The domain, x is an element of all real numbers. The range would be simply y equals 3, because it's a straight horizontal line. And there are 0 x-intercepts. Of course, if you have f of x equals 0, how many x-intercepts would there be? An infinite number. Very, very good. Yes. If this blue line was actually on the x-axis, every single point on that line would be an x-intercept. And there's, of course, an infinite number of points on any line, no matter the length. Did you know that? Now, if you think about that, that would blow your mind. If you have a really short line, it's the same number of points as if you have a line that's 10 miles long. Because it's an infinite number, even though it's a finite distance. Ooh, mind blown. Okay, think about that later. All right, degree 1. What about degree 1? Yeah, just let that marinate for a little while. All right, degree 1. This is a straight line. It's linear. Okay. The end behavior, if the coefficient right here, this number 2 right there, do I need to zoom in? If that coefficient is positive, it goes from quadrant 3 to quadrant 1. If it's negative, it goes from 2 to 4. Got it? Okay. All right, what about degree 2? That's a quadratic function. That is a parabola. You guys know about that. And what do we know about this? There could possibly be a maximum of 2 x-intercepts. And the end behavior, if the leading coefficient is positive, it always goes from 2 to 1. Okay, now, and some of you may say, because I've had students ask this before, they say to me, Mr. Maxwell, I can draw a parabola that starts in 1 and ends in 1. What do you have to say about that? Yes, it goes on forever upwards, but it also creeps over here to the left forever and ever and ever as well. So of course I'm extending this, right? So it will eventually end up crossing the y-axis here. And this of course goes up and to the right forever. So it, yeah, even though you draw this portion of the parabola, it looks like, hey, it's 1 and 1. It actually will eventually spill over into the other quadrant. Now, will it ever end up down here in this quadrant or this quadrant? No, because it's going upward forever, not down. It won't flip around, go down. Okay. You guys are doing good. You have any questions so far? No, we're all awake still? Hi. Okay, good. Stay awake. Cubic function. All right, so here we go. This is the general shape of a cubic function. Now, this little mountain here and this little valley, obviously that changes a lot, just depending on the terms. But the end behavior is the same. The number of maximum intercepts would be the same as the degree, 3. Okay. Notice that you cannot have 0 x-intercepts for a cubic function, because the end behavior straddles the origin, right? It straddles the x-axis. So it has to cross at least once. Here's degree 4. They start to look a little bit funny. You know, here these shapes are pretty funny, but end behavior is the same for all even degree polynomial functions. Notice this is even. Okay, just the same as this is even, and this is even. So there's some similarities there. All right, do you have any questions for me? Yes, 0 counts for even. Yeah. Because up here it's 2 to 1. End behavior has 0 intercepts. So, yeah, this even degree. Okay, any other questions?